Okay. Now, this particular question that we're dealing with first ask us to explain Fleming's left-hand rule. So, what is Fleming's left-hand rule? What's the use of Fleming's left-hand rule? Now, you know that in a magnetic field or an electric field, that a particle will experience a force, right? Now, that particle is also moving. We assume in most cases it's moving. So, what Fleming's left-hand rule allows us to do is to predict one of three things given the other two. It allows us to either predict the path of the particle, the direction of the force acting on the particle, or did I say the path of the particle? Okay, or the field that is acting on the particle, the direction of the field. So now, Fleming's left-hand rule, basically, we hold our middle finger, right, index finger and thumb at neutral right angles like this, right? So now, when we hold our fingers at mutual right angles, this is how it goes exactly. The thumb would be the force acting on the particle. The index finger gives you the direction of the field, right? The middle finger gives you the direction of the particle, right? So, essentially, what we try to do is we orient our hand in any of these two knowns. In some cases, we know the field and the direction of the particle. However, one must note that Fleming's left-hand rule is defined for a conventional current or conventional charge, and we know that consists of positive charge, right? So now, say you were an electron, you just use Fleming's left-hand rule anyway, but just reverse the final result. In other words, now for example, say there's a field acting towards you, and then say the particle is going that direction, right? So the particle is going that direction and there is a field towards you, that means that a proton would go up, right? But that's for a proton. Now you are assessing for a proton and a positively charged particle. Then what say an electron? It has an opposite charge, so we go the opposite way. So we go down instead, because we just assess for a positively charged particle. Okay, that's basically the Fleming's left-hand rule. So now quickly, let's just look at this. Now, essentially this question was just asking us to apply what we knew by essentially determining the path of a particle in a field, and that particle is an electron. So as I said, we use Fleming's left-hand rule. So set your fingers at mutual right angles, people. So now the direction of the field is towards you, right? Towards you, and oh, this is so hard to manipulate. The direction of the field is towards you, right? And we know that direction of the particle is actually that direction, right? So we orient our hand like that, and the field is still towards you. Alright, this I'm getting pretty twisted, but if you test the hypothesis, essentially what you got would have been for a proton, so you just reverse it for the electron. As a matter of fact, the question actually asked about a proton, so the direction of the electron is up that way, which can be proved using Fleming's left-hand rule. The proton is down, right? Down. And it's deflected, because it still has a vertical component, so while it's going across, it's going down, right? So it goes across and down. So now, let's see what else now. Now, it asks what work is done on the electron in the magnetic field. Then now intuition or from previous knowledge, we know that the particle moves in a circle in the magnetic field, right? It moves in a circle. So now that's a given. So it moves in a circle now. What that means is that there's a centripetal force acting on it, right? If there's a centripetal force, we know from basic fourth and fifth form work that the centripetal force does no work. Hence, no work is done on the electron. Another way to reason this is that the force and velocity act at right angles to each other. Whenever force and velocity are acting at right angles to each other, that would mean that no work is done. You can go and prove this by using the formula, I believe, what F force equal work done is equal to force times distance times cos angle. Now anyway, we move on to the next question, and this question was essentially asking us to prove the formula for the curvature, the radius of curvature of the charged particle in a field, right? So now essentially, remember we mentioned that centripetal force. That centripetal force now would have been equal to mv squared over r, where v squared over r gives you the centripetal acceleration, so it's mass times acceleration. And then we know that in the magnetic field, the force on a charge is given by qvb. In this case, the charge is an electron charge, so it's bev, right? Remember bev and bev. Now we're going to solve for r from that equation above. So now the reason we have this again is that because we assume that the force acting really the one due to the magnetic field, but it causes a centripetal force, which is of course is equal in magnitude to it, right? Newton's basic laws of motion. So now we solve for r from that. When we solve for r, we get that, and then yeah, that's basically it. Now the question also asks for us for the path that the electron would take, or more so how much it would curve. Sorry, it's show the path of an electron through a magnetic field, given that the magnetic field goes to half of its magnitude. Now, if it goes to half of its magnitude, try to remember that formula. You can pause the video at that formula, go back and pause. No, but essentially what happens is that if the magnetic field is halved, there's less force exerted on the electron, so then it moves with less curvature. It's less curved, right? That can be proven with the formula. So hence it's deflected less because less force is exerted on it. That's all. And then here comes the Whopper. The final question. Now it talks about particles entering an electric field under the same conditions. Now one is an electron and one is some other charged particle with the same charge of the electron but a different mass, and you're supposed to find that mass. How do we find that mass? Now we know that they both entered an electric field V. They have the same charge. So naturally the work done on both is the same because their charges are equal, right? Because you know the work done is on a charge in an electric field is given by the charge times the voltage, or yeah, that's basically it. So now we assume that all of this, based on law of conservation of energy, is converted into kinetic energy. So now the kinetic energy of anybody is given by half mass times the velocity squared. So now all that simply means is that we're going to have that this times this is equal to half mv squared, which is just giving the kinetic energy of the mass x, and same thing with the electron. And then we know that qxv is equal to qev because the charges are equal, which is equal to ev. So hence these two things, the kinetic energies must be equal. So now we simplify that formula: half mx vx squared equal half mev squared. Then we just multiply by 2 on both sides. Now here's another formula we can come up with. By the way, this is a simultaneous equation. It would be good if you knew how to solve simultaneous equations. So also in the magnetic field, we from the earlier proof, we know that the radius of curvature is given by r is equal to the mass of the particle times the velocity of the particle divided by the field strength, the field then magnetic flux density times the charge, right? But in this case, we know the radius of curvature is 10 centimeters for the electron and 15 centimeters for the one with mass x, the particle with mass x. Now we know that 10 centimeters must be equal to MeVe over the flux density B times the charge E. We know that since x, the particle x has basically the same charge, that we know that everything will be the same except its mass and its velocity. We don't know those. Now we can just divide those equations into each other. Basic math again. Divide those equations into each other, and we get that, right? So divide the equations into each other. Now finally, it is simplified to 2/3 is equal to MeVe over mx Vx. So we have the ratio of, well, actually that's their momentums. We have the ratio of their momentums. You don't have to look at it that way. We have the ratio of their products, the product of their masses and velocities. So now, and then we can cross multiply and we get, this is the formula here. Now we have two equations. Remember the one for kinetic energy? So we have that one and that one. We divide this one by this one. We get something like this. We end up with Vx over 2 is equal to Ve over 3. So hence we can find the ratio of their velocities. How does this help? Ve over Vx is equal to 3 over 2. Remember, this is little than the formula we got from dividing the ratios of, well, finding the ratios of their radii of curvature. So now notice that in this expression Ve over Vx, ignore everything else. So now we know what the value of Ve over Vx is from that, right? So let's replace that into this equation. When we replace it into this equation, we get 2/3 is equal to 3 over 2 times Me over Mx. Hence, we finally get, when we transpose 4 over 9 is equal to Me over Mx. What is it saying? That the electron is 4/9 mass of X, right? And then all we do, we transpose for Mx, and we get Mx is equal to 9 times Me over 4. We know that the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So now we just do a replacement here and put it in our calculator. I don't have a calculator, so that is it.